So today we're going to be talking about gravitation. We're going to be doing two sections, and that's just because these ones fit really well together, and the first one's really short. So I should be able to cover these no problem today. So, and lots of it's going to be repeat from last year, and what we did already in dynamics. So Newton discovered that gravity attracts any two objects depending on two things. So this is going to depend on their masses. And what? Yeah, the distance between them. So distance apart. So there's some jargon that's in here. I'm not necessarily expecting you to know this. But basically this says Fg is proportional to the two masses, meaning as mass 1 or mass 2 increases, the Fg will increase. As the force increases, that means one of your masses is increasing. Actually, no, just if the masses increase, the force increases. The alpha means that it's proportional to. Just means as one goes up, the other has to go up. And it's inversely proportional to the square of the distance, meaning Fg is proportional to 1 over r squared. The reasoning you do this just is how they figured this out, which you saw last year. So this is the equation that you've seen already. G, this is your gravitational constant. 6.67 times 10 to the negative 11. I don't remember the units for it. Let's see, it's newtons meters squared per kilogram squared. Not that that's super relevant, but that's just what the unit is. And then M1, M2, these are your masses. And r is not the radius. Yes, on the shelf there's a 3 partitions, and it should be at the top on the wooden shelf. Yeah, should be that one. You're welcome. And r is the distance between centers. Salim. So r is not the radius. Please don't get confused by that. R is the distance between the centers. So let's give this a go. These questions are going to be pretty straightforward until we get to the centripetal acceleration part. So let's calculate Fg. You have two masses, you've got a radius, so this is pretty straightforward. You're just plugging the numbers into the equation. So you've got this. I've got the two masses of 75. My distance between the centers is already in meters, so I just plug that in. I'm not going to write out all the numbers. You can figure that out. -7. So if you plugged in those numbers, you get this. So this is pretty small. This is normal. You've got really small masses, so therefore the force is going to be really small between them. Any questions on this one? Yep. Yes. Yes. So the capital G is going to be the 6.67 every time. Doesn't matter what masses, doesn't matter if you're on a different planet. Capital G is known as the gravitational constant, and it stays the same no matter what. I showed you a question like this in last year. This is a very typical kind of question. So we talked about here's a weight on the surface. What's going to happen if my mass triples and the orbital radius is doubled? So this is a very common question. You'll see this lots. Essentially what you're going to do for this, write out the original equation, We don't know any of these numbers. Well, technically, I guess we know it's the Earth's surface. But I can give you this without telling you anything about the Earth. Or I put it on a different planet and tell you no information about it. All you know is that this is 9,000. Then I'm going to have a new weight. This is what we're looking at. So FG new. And what changes? So I'm going to triple one of the masses. Doesn't really matter which one. And my radius is doubled. So we can solve this without knowing a single thing about masses or the radius. Because I know this, all these variables together equal 9,000. So if I can find these original variables down here, I know that equals 9,000. So I'm just going to separate all the numbers to the front here. So I'll have this 3 GM1, M2 over, expand out the squared, I'll have 4R squared. So here, in this box, that equals 9,000. So I'm just going 3 over 4 times 9,000. This should seem familiar from last year. I can't do that in my head right now. 6,750. So this kind of a thing is very common, where I tell you, here's the original weight, and I'm going to change the mass and change the radius, or the orbital radius. So just be aware this is highly likely to show up at some point, and it looks like you have very little information to solve it, but you actually have everything you need. Any questions on this? Mm-hmm. New. The new FG. Yeah. Any other questions with this one? Yeah?
What's the difference between this MG and the FG?
You mean where it's m times lowercase g? So that's if you know what the lowercase g value is. So on this case, if it's the Earth's surface, yes, you could figure it out, no problem. So I could solve for what's the mass of the object, and I could solve it in a different thing. But I can easily tell you the method of solving this is going to be the same thing if I take this out and say on planet X's surface. Yeah. Yeah. New. The new FG. Yeah. Because it's asking how much does it weigh on the, if you do these things. So it's just the new FG. Anyone still writing this out? Again, I'm going quickly through this because this stuff is mostly review so far. Do you remember the difference between mass and weight?
Weight is mass is the amount of molecules, weight is
Yeah, so which one changes? Weight. Weight changes, mass is constant. Good, so you remember this. So mass is the amount of matter. And it does not depend on where you are, so it's constant everywhere. Whereas weight is gravitational force.
time is mass.
No, just the gravitational force. It's the gravitational acceleration times the mass. So gravitational force and depends on location.
Surrounded are the different spaces on Earth with different gravitational acceleration?
Yep. Yeah, the average of the Earth is 9.8, but depending on where you are, that 9.8 changes.
Is it like, does it have to do anything with altitude?
Yep.
Like the higher you are?
Yeah, it depends on this equation. So the masses can stay the same, but depending on your distance from the center, it changes. So the Earth is not a perfect sphere. Around the equator, it's wider than it is at the poles. So if you're at the poles, you're going to weigh more than if you're at the equator. So how this now relates to our new unit is just this little part at the bottom. So if you've got a satellite in orbit, a satellite just means something that is orbiting around. So we could have the moon counts as a satellite, we could have satellites count as satellites, we could have an astronaut that's stuck in orbit around the Earth counts as a satellite. Anything that is stuck around the Earth, basically. Not something that is potentially able to be stuck around the Earth. So essentially what we've got is something like the moon is basically constantly falling towards the Earth. But it doesn't actually fall to the Earth, rather it falls around the Earth. So this is a different concept. You can wrap your mind around it. If the moon was just sitting there, it wasn't actually moving around the Earth, what would happen? It would crash into the Earth, right? Here's the Earth, here's the moon. What would happen is if it's not moving, the moon just collides with the Earth. However, the moon has some sort of a speed. So if you remember from projectiles, if we looked at a constant, what we've discussed before, so if I shot something in this direction, what would happen? If I'd shot a bullet, it would go and the bullet would fall. Right? There would be recoil on the gun. What happened if I shot it fast enough that as it fell, it also curved around the Earth because it's going so fast? The bullet would be in an orbit going around the Earth. So, nope, it would keep orbiting. That's what the moon is doing. It's just farther away. So here's the Earth, here's the moon. So the moon is falling, but it's moving as it goes towards it. So as it spins around, it's constantly falling towards the center of the Earth. But because it has some velocity that's carrying around the edges, it's never actually going to hit the Earth.
So if it slows down, if it goes faster, we die?
If it slows down, it will hit the Earth. If it goes faster, it might leave the orbit.
In both situations, it's bad, right?
I don't know how to speculate what would happen if we no longer had a moon.
If we didn't have a moon, we said,
I think we wouldn't see it really cool.
This is a discussion for another day, because I don't know what would happen.
unless you wouldn't see at night. Oh, yeah, I'm going to moon
So this is what's happening. So here's the moon. Here's the Earth. And essentially what I've got between these two is there's this force of gravity. So here's its velocity. Here's the force centripetal, which is also in this case equal to force of gravity. But this is what's happening. The moon is moving, but it's also falling towards the Earth at the exact same time. So if, what are we talking about? So if you have a person that's just floating in space, and they're in an orbit, they're going to feel weightless because they're basically constantly falling towards the Earth. It would be the exact same feeling if you are dropped from the atmosphere and you're falling downwards. You have that acceleration towards the center. Which part?
What is the circumference which?
Earth, moon, orbital path, velocity, force. So velocity is perpendicular to the circle, just like we've always seen. Force is always towards the center. So we've seen multiple cases. We've talked about tension in a rope that causes an object to stay in the middle. We've talked about force of friction in terms of cars going around unbanked curves. We've looked at the normal force. If we've got a banked curve, we've got force of gravity and tension in vertical circles. Now we're extending this now to gravity. So that's what this question is all about. We've got a Earth satellite is in a specific orbit. In order for it to maintain that orbit, we want to look at what does that speed need to be. So here's the Earth. Here's our little satellite. It wants to travel around the Earth like this. We want to know what speed is at. So if I looked at the forces acting on this object, what forces do I have? So force centripetal is a net force. So I wouldn't draw it in a free body diagram. Just force of gravity. So the net force, according to the center of the circle, is Fg. And then I solve for speed.
Speed.
Yep. So Fc, if I want speed, I need m.
Squared over.
Yeah. Fg, in this case, capital G, m1, m2 over r squared. Conveniently, these r's are the exact same. So this r is the radius of my circle. This r is the distance between the two centers. In our specific case here, those are the same. So an r and one of the r's from here cancel. So if, which mass is this? Is this m1 or is this m2?
Either.
It makes a difference. So this is the mass of the satellite. So traditionally that's m2. So we actually don't need the mass of the satellite. You'll find this is a common occurrence. So in order to solve this, v, our speed, is g m1 over r. And I need to take a square root in there. So notice, well, I can plug in the numbers. We know the mass of the Earth. Well, you should know the mass of the Earth. It'll be on the, it should be on the formula sheet. We have the orbital radius.
6.6.
So this is the speed at which something needs to be orbiting around the Earth at this specific radius in order to maintain that orbit. Notice, what does this speed depend on? The radius and mass of the Earth. So it doesn't matter what the satellite is. Doesn't matter what the mass of the satellite is? No. Yeah. So the speed is going to be the same no matter what kind of satellite you have. So as with previous questions you've seen in this set of notes, often masses are not given, which means it's just going to cancel out at some point.
So it was like the same distance, the satellite was the same distance as the Earth is from the moon, and it was the same velocity as the moon?
Yep. So if this satellite was instead the moon, same speed. If this satellite was Jupiter, same speed. It would probably have a slightly different effect, but it doesn't matter about the mass.
If there's an instance where another force is acting on the object that's not just a force of gravity, would that still apply as a constant?
Yes, so there would be something else that would happen if you include another force. In a gravity question, you won't see that, simply because you're rarely going to have another force that's going to act on this object. But in the last section, there's cases like that. Or in the section before that, there's going to be cases like that.
You're going to ask us, like, the calculate the same thing with the Earth?
What do you mean?
Like, rather than calculating the acceleration, the velocity for the satellite,
Mm-hmm.
you calculate the velocity for Earth?
No, so it wouldn't make sense to solve for velocity of the Earth in this case, because the Earth is not orbiting the satellite.
That's the first time fly off over the Earth.
Yes, yeah. So I could ask you, what is the speed of the Earth traveling around the Sun? That would be something viable. And then I don't care about what the mass of the Earth is, just what the Sun is.
How do you cancel the distance between the centers and the radius?
Because in this case, they're both the same. So this distance from here to here, that is my, my radius of the circle that this satellite is traveling. And it's the distance between the two centers. So that's why it's both in this case. Any other questions with this? Yeah?
I'm sorry, but mathematically, how would they cancel out the columns?
You just times both sides by r. So I times it by r, that gets rid of this, times this by r gets rid of the squared. So that's that. So I can continue on with this because this is basically just ignore one of the masses. And this is going to be the same thing. So it just piggybacks on the other one. The first page here is just let's talk some concepts. So do you remember some ideas about a gravitational field? I compared field strengths to fires. Do you remember something like this? So if you wanted to experience a greater amount of heat, what do you do? Get closer or make the fire bigger, which is probably what you were alluding to. So if you've got a fire, it essentially is emitting a heat field. Now it's not really, there's no such thing really as a heat field, but we can just pretend there is. So as you approach the fire, the field strength will increase, so the heat increases. And as you increase the size of the fire, you have the same thing, heat increases. So we talk about, I compare it to fire because that's something you've experienced more. You've never, well, I'm assuming most of you have not gone into a satellite and tried to experience what gravity is in orbit. Once or twice, yeah. So what you're going to do over the next break, right? So this is what a field of influence is. It's an area where you affect something without actually touching it. So you can affect people around you. You can imagine, this is a far-fetched idea, but you can imagine you have a field of influence around you with your words. So what you say affects those around you. That's kind of like a field. You have a field of your voice around you. The field is described as a... No, this is just an area of influence. I already said this. I just didn't fill it in. Yeah. Do you think it matters direction?
No, it's a
It sure does matter. If you're being pulled towards something or pulled away from something, it makes a big difference.
negative or positive. Negative or positive initial addition. You go far.
It makes a huge difference for those who are trying to orbit around the Earth.
Yes.
If the Earth is pushing you away, it'd be rather difficult. Well, it affects you too with your if you want good cell phone coverage. So, field is going to be described as either vector or scalar. So heat will be more measured by temperature, so that one's a scalar. Whereas gravitational force fields are vectors. So it matters the direction. So we can draw these vectors as arrows. So if I wanted to look around the Earth and see what is its gravitational field, gravity always pulls. Gravity doesn't push. So if we looked at the field around here, you'd have arrows that are moving towards it, and they are uniform. I shouldn't say uniform. They are, it's not a constant field because it changes as you get farther away. It's the densities at specific radiuses are constant.
So how do you know that the Earth is pushes away and normal force keeps us on the Earth?
How do I know? You can try it. Drop something.
Yes, I mean the normal force is pushing us towards the Earth.
If you wanted to redefine terms, then yes. But that's the only way you could think about that. Because if you're saying normal force pulls towards the Earth, you're just changing the definition of what gravity is to be a normal force. Because by definition, the normal force is the force that is perpendicular to the surface.
Not up. They decided. I learned. Normal
Good.
force can go like this, right?
Normal force can go sideways, that is right, depending on if your surface is vertical.
Yeah, Danny.
So like I said, lots of this is going to be reviewed. That's why I'm just whipping through it. So you remember this equation, Fg equals mg. So therefore, g is equal to Fg over m. Yeah, lots of this is reviewed from last year. So you know what each of these things are. G has two names, acceleration due to gravity and gravitational field strength. You need to know both of those. Essentially on the Earth's surface, we can assume it's 9.8. However, this only works if you know either the force of gravity or the mass. Often you do not. So we can just take our now definition of Fg, and we can write G equals, change what Fg is. And what mass am I dividing by in this case? Is it the Earth or is it the satellite? Well, let's think about this. So this is going to cancel one of the masses out, and I'm going to be left with this. Which mass does the acceleration due to gravity depend on? The satellite or the planet or whatever that is? The Earth. So this has to be mass 2. And you're left with the mass of whatever is causing the gravity. Or I shouldn't say that causes gravity because everything causes gravity. It's more what is the acceleration due to gravity that we're looking up? Are we looking for the Earth's gravitational field strength? Are we looking for the satellite's gravitational field strength? Whichever field strength we're looking for, that's the mass you use. Yep.
What's the difference between gravitational acceleration and
So no, yeah, they're the same thing. Gravitational acceleration is your acceleration due to gravity. Yeah. Now let's try more questions. Everyone loves questions. So, gravitational field strength of the moon. So we want to know what it is for the moon, so I need to use the moon's mass. Let's try it. Let's see if it is. Squared. So those of you who like to write your own formula sheets, there are four constants that you should have. You need the mass of the moon, radius of the moon. You need the mass of the Earth, you need the radius of the Earth. You will want to have those written out on your formula sheet. I am starting to say no. If you're going to take the time to make your own formula sheet, you need to be diligent enough to use everything you can. It's a blessing and a curse. Nope, it's a blessing and a curse. You can write down a lot more than what's on the formula sheet. However, if you forget something, that's on you. I give them, not all the formulas are on that formula sheet that are in the notes. You can take a look at it, yeah. Sure, if you want to. Yep. The radiuses, yeah. What do we got? Satellite orbits the Earth at this radius. What's the orbital period? Okay, so again, for this one, we've just got the same FC equals FG. Oops. feel like I could carry on a conversation with just those of you who are listening online. Oh my gosh. Since the entire class is talking at the exact same time, you're the only ones who can actually hear what I'm saying. No one else. So with this is with the object. Do I need to send you outside onto the stairs? And yet you're the one who is talking the last. Notice how trying to help out and take over the teacher's job doesn't help. So, in doing this, we can cancel out the masses. So often you'll be given something like this, and the FC is often just going to equal lowercase g. So what I've got in this expression, notice this is the same thing as AC, and this side is the same as lowercase g. You will find this is often the case, because you're going to be canceling out these masses anyways. So in a situation like this, yes, you could do Fc equals Fg, but you also know your acceleration due to gravity is equal to the centripetal acceleration. Because you only have one force acting. You've just got Fg. So when you're dealing with gravitational problems, this is often going to be the case. Because the M1 here and the mass here, those are always the same. The only way that this would not work is if you've got another force acting. But in gravity, you usually don't. So for this, I've got the orbital radius. I've got it here again. I know the mass of the Earth. I need to solve for t. So this is just doing some algebra. I'm going to assume that you know this. Yes, t is tension. T is period. Yep.
Why did we use the log equation for FG? Why don't we just say FG equals MG?
Because we cannot use just mg because we're not on the surface of the Earth. If it said it was on the surface of the Earth, I could use mg and just use 9.8.
And the mass will cancel out. The mass of the
Cancels out, yep. Mm-hmm.
So M1 here is Earth.
Mass of the satellite. Or, sorry, yes, M1 is, in this case, yeah, I switched them out. M2, here's the mass of the Earth. Traditionally, M1 is the Earth. And then this would make this mass 2. Yeah, I just switched them. Yep.
Where did the mass for the satellite come from?
You don't need it. They cancel.
The other ones, G and
Yeah, I accidentally switched them. This should be mass 2. And it should be like that. So one last thing here we need to discuss. We need to look at geosynchronous orbits. Geosynchronous. Geography, study of the world. Synchronous, synchronized.
Synchronized.
Have you ever seen synchronized swimming? Same timing. See, he knows what he's doing. Synchronized swimming is crazy. Not as easy as it looks. So let's talk some concepts here. So the orbital speed of a satellite will depend on the strength of the gravitational field at that orbital radius. So let's consider two situations. And think about which satellite travels faster in which case. So if I've got satellite A orbits at twice the orbital radius of satellite B. Ready? Shh. So let's think about this. One of them is at twice the orbital radius. So which one's going to move faster? The one closer. Why?
Because it's not
Moving into the center,
G bigger than the one.
Yeah. So it depends on the strength of your gravitational field. So whichever one has the bigger gravitational field, that's going to move faster because you have a bigger acceleration. So why does this one work? Well, because it's closer. Because it's closer, FG is bigger. And because FG is bigger, it has to move faster. If it doesn't move faster, it's going to, its orbit will decay. How about the second one? I've got two satellites at the same orbital radius, but one of them orbits around the sun and one orbits around the Earth. A or B? A. Why A? Because the sun has more mass, therefore FG is bigger, therefore it has to move faster. So in order to maintain an orbit, you need to be moving at a certain speed in order to stay at that place. So if the FG is bigger, you obviously need to move bigger so that you don't fall into orbital decay. What is this saying? An orbital period of satellite depends on mass, radius, therefore some orbital distance. Such as satellite geosynchronous or geostationary. Oh yeah, okay, so something that is geostationary means it's essentially staying above the same point on the Earth as the Earth rotates. So that would mean like if I was the Earth and I'm rotating around and the satellite's here, it's going to rotate at the same speed I'm rotating at. That's what it means to be geostationary. So you can have a satellite that is orbiting at the exact same speed as the Earth spins. So we want to figure out what is the orbital radius of a satellite that is above the Earth's equator. So let's figure this out. So here's the Earth. Here's our satellite. It's at some radius here, and that's what we're looking for. So we know nothing about the satellite, but conveniently we already know for most of these cases we're going to end up with this. So I don't even need to deal with the forces. And I want the radius, so I need to use whatever one is most convenient. So do I do v squared over r, or do I do the 4 pi r over t squared? Why? We don't have the period, but I don't have velocity. Well, in the second one, I'm asking for the speed, so it's a good assumption that we're not going to solve for the velocity in this case. That's going to be for this side of the equation. Yeah. And this one we know, this one's just gm over r squared. So we need to solve for the radius. So I'm going to show you the algebra for this just so you can see where it comes from. So this goes to, I'm going to multiply r squared onto this side, get r cubed, gm t squared over 4 pi squared. Do I have everything? Do I have capital G? Yep, obviously. Mass, what's the mass in this case? Earth, okay. What's T? T is, no, T is not 0 because then the radius is 0. What is T? What variable is T? No, it'll just cancel out with everything. T is the time it takes to do one revolution. If I am geostationary, that means this satellite is orbiting at the exact same speed that the Earth is rotating. And what is the amount of time it takes for the Earth to do one full rotation? 24 hours. So I can figure out what t is. We can just use some unit analysis. So the period is 24 hours. I'm going to times it by 60 because there's 60 minutes per hour. We'll cancel out hours times 60 seconds per minute. So this is 864.00 seconds. Fun fact, if I remember correctly, did you know that the number of seconds in I think it's seconds in a year, is basically the same order of digits as pi? 314 something. If you're curious, give it a try. The digit's the same, not 3 and then point something seconds.
How many?
Oh, yeah. 31536.
It's pretty close. Anyways, so I now have the period, I know the mass, so you can solve for r. It's going to be 4.2 times 10 to the 7 meters. Now to get the speed is the easy part, because I know what speed is. All right, any questions with this?